All right, so we're learning about parametric equations. Let's do some examples. First example, maybe one of the simplest examples of a parametric equation describing a curve is the unit circle. 1, 1, -1, -1. The unit circle, if you have a point on the unit circle, what we've learned about trigonometry now is that the coordinates of that point x, y are given by the cosine of the angle and the sine of the angle, where t represents this angle right here. If t is in radians, it also is exactly equal to the distance measured along the circle, right? So this right here gives us, just hands us a parameterization of the circle. I use the word parameterization. If you have a curve and you're trying to describe it with parametric equations like this, then what that's called is a parameterization. So a parameterization, here we go, that's how it's spelled, of the unit circle would be x is cosine of t and y is sine of t. Now, as a domain for this parameterization, what you want is a range of t values. And you could use all real numbers, because any real number gives us a valid angle to give us, to describe a point on the unit circle. But a simple domain you can use here, if you just want to describe the circle, wrapping around the circle one time, you can just use the range, the domain from 0 to 2 pi, like that. And technically, I guess I did equal on both sides, so maybe it overlaps at the point 1, 0. But anyway, that can be our domain that gives us the circle. So that is a nice simple parameterization of a unit circle. And I'll show you later how you can take that parameterization and adjust it to give you a circle of any radius, or in fact, a circle centered at any point, or in fact, an ellipse centered at any point. We'll get into that soon enough. Here's another simple example. What if I just want to describe a linear function? Let's say we have this, y equals, let's say 0.5 x plus 1. Hey, it's a slope, it's a linear function, it's got a slope, it's got a y-intercept. Let's see if we can describe that with a parameterization. You've actually done this before. When you solve systems of equations and you get that the solution is dependent, that means that there's infinitely many solutions and they lie along a line. And it's traditional, it's to describe those solutions with a parameterization, where you say, let's go ahead here and just let x equal t, right? Then a parameterization can be written like this. X is t and y is, well, you guessed it, 0.5 t plus 1, right? Replacing the x with the t. So that's our parameterization. In its domain, well, if we want to describe the entire line, infinite line, off in both directions, since the x is exactly equal to t, normally the domain of this linear function in x and y would be x values ranging from -infinity to infinity. So I think we're going to do that with our t as well. Not equal. Duh. Less, not equal. So that range of t values, or that domain, is going to stay the same. Let's do one more example. Let's say you have a parabola, but your parabola is on its side, like this. So this is the equation x equals y squared. Well, the way that equation is set up, it's kind of like x is a function of y. Instead of y being a function of x, it goes the other way. So what you want to do here is just go ahead and let y equal t. Okay, then your x will be t squared and your y will be t. There you go. And your domain again, if you want to describe the entire parabola, you better have y be ranging from -infinity to infinity. So there are 3 examples of parameterizations of curves. In other words, taking graphs and describing them with parametric equations. And in each case, we have the x function and the y function and a domain. And the domain part is usually sort of implied, but sometimes you can specify what the domain is if you just want to describe, for example, just a segment of a curve. Let's actually do an example of that. That makes me think. I want to do an example of that. Let me think about this for a second. No, actually, I won't do an example of that today. I was thinking about something that we do in Calc 3, but it uses vectors. So maybe we'll talk about that later.